Yes, it works. All right, so we are still on parametric calculus, the derivative version, and we've been kind of alluding to the particle motion stuff, but parametrics doesn't always have to be about particle motion. But it's especially useful when you have particle motion through a two-dimensional plane, okay, not just a straight line. So here's kind of a review of some of the stuff we've already been talking about. Your horizontal and vertical velocity component vectors. So x prime of t, also known as dx/dt, that's the rate at which your x-coordinate changes with respect to time. And y prime, or dy dt, is how fast your y-coordinate changes with respect to time, the parameter. If you combine the information that we've been talking about together in an ordered pair type fashion, that's when it becomes vector calculus, okay? So let's define what we have going on here. We use S typically for position, from the German verb strecke, which means what? No, distance. Yeah. So anyway, if you put a little arrow above the S, that's kind of vector notation, okay? And it could be, typically, we write a half arrow like that. That's how we would write it by hand. But it could also be, if you have the time, you can make a double-headed arrow. It does, yeah, with kind of a gutter or something. So anyway, and the other thing that we sometimes do, typically do, is we write the position vector as an ordered pair, and we use chevrons, which is what we call those, instead of parentheses. So x of t comma y of t is going to be the position of the particle as it moves through the coordinate plane at any given time, t. Now, because it is an ordered pair, sometimes you may not see it written in the chevrons. It could still be typically written as an ordered pair with parentheses. That would be the position of the particle at any given time t in the coordinate plane. Similarly, if you take the component derivatives, x prime and y prime, and you write them in an ordered pair fashion, you get the velocity vector, all right? And again, it's an ordered pair, but it breaks it down into the two components. So you have v vector is equal to chevron x prime of t, y prime of t. But again, sometimes you'll see it written without the chevrons. And then same kind of idea, if you take the second derivative of both x and y, you get the component accelerations, and you can write those also as an ordered pair using chevron notation or sometimes parentheses, all right? So that's what the note says. The vectors may or may not be contained within the chevrons. All right, so to review from yesterday, dy dx is still your rate of change of your vertical with respect to your horizontal, but it's going to be a function of t now. It's what we called yesterday the tangential velocity. If it were to follow along a curved path and then suddenly break out of that path, it would fly off in that direction at that speed. But that's actually the speed that it's traveling around the curved path. And the second derivative is still the curvature of the graph, but it's also the acceleration as a function of time. Okay, so shifting gears here a little bit. The absolute value of velocity, we know that quantity to be called what? The absolute value of velocity. Speed, yeah. Well, if you take the absolute value of a velocity, bless you, vector, what does it mean to take the absolute value of something that looks like an ordered pair? You just take the absolute value of each coordinate? Not necessarily. Okay, so that looks a lot like absolute values, and you can kind of think of it as an absolute value because that still does give you the speed, but it's actually called the norm, okay, which gives us what we call the magnitude of the velocity vector. So sometimes you might see it written with like a double absolute value symbol because it's not really the absolute value. It's going to be a single number, okay, that represents the speed of the object in a certain manner. So how would you end up finding the speed of the object? Well, let me show you a real quick diagram. If you break down your vectors into components, okay, this could be your x prime vector, and this could be your y prime vector. So maybe at some point you learn how to add vectors by the head to tail method. You would slide one of them's tail to the head of the other one like that. And now you have them running in sequence. That's called the head to tail method. Then you would draw a new line from the tail of one, the fixed end, to the head of the other one, and we call that the resultant vector. The resultant vector, okay? So if you have an object that's traveling through space and you break it down into its components, when you add them together, you get, first of all, the distance that it's actually traveling around the curved path, and the length of that resultant vector, okay, which I'll do that. That's called the norm, and I'll just use R for resultant vector. That's going to be the speed that it's traveling in that particular direction. So think about it. If you knew the length of x prime and you knew the length of y prime, how could you find the length of the resultant vector? Pythagorean theorem. Very good. It's going to be the square root of, when you solve for it, x prime squared plus y prime squared. And that's exactly what it is. Okay? And I use dx dt instead of x prime of t, but it's the same thing. So the norm, which is the absolute value, really, of the velocity vector, is a single number that gives you the speed of that object in that direction. And it's just the Pythagorean theorem. It's the square root of x prime squared plus y prime squared. Okay? Very important. We call that the speed of the particle in that direction, or the magnitude, or the length, or the norm. It has all kinds of different names. Now, if we go back to particle motion, we were on a straight line. Let's review this. The integral from a to b of a velocity function with respect to time always gives you what quantity? Is that total distance? What if velocity is negative? This is net distance, which we call displacement, right? The integral of velocity in general is displacement. But if I integrate the speed function, which is the absolute value of that function, remember what that does, the absolute value transformation takes all the negatives, if there are any, and makes them positive. Now when you integrate straight across, you're finding the area. So there is no cancellation. That's what gives you the what? That's the total distance traveled. That's really the same idea whenever you integrate the speed function, whether it's in rectangular coordinates or, as you'll see here, in parametric and vector. The integral of speed is always going to be the distance traveled. Always going to be the distance traveled. So, if this truly then represents the speed of an object at any given time t, if I integrate that function from a to b, I end up with the total distance it travels, which we learned yesterday was also known as the what? The arc length. Yeah. So there's your arc length formula from yesterday. But again, in the context of particle motion, it is the length, or the distance, I'm sorry, that the particle will travel through the curved path from time equals a to time equals b. All right? So kind of a double thing happening there. This is still the speed function, which is just the Pythagorean theorem. When you integrate it, you get the length of the arc, or the distance the particle travels. All right. You ready to try out in a vector context? Is parametric and vector really the same? Okay, yes, good. Example 8, no calculator. A particle moves in the xy plane. So whenever you see something like xy plane, that's kind of your cue that it's going to be either a vector or a parametric equation. Because AB particle motion is just a particle moves on a horizontal line or a particle moves on a vertical line. One dimension only. This is two dimensions. So that any time t greater than or equal to 0, the position of the particle is given by those two coordinates. All right? So we can actually write, if we want to interpret it in vector style, we can create a position vector, call it S arrow, and it would be t cubed plus 4t, comma, t to the fourth minus t cubed. But we don't necessarily have to do that. We could think of it in the parametric realm, or we can kind of now think of it in this new vector realm. Really the same thing, just packaged differently. And technically, if you want, you can call that not just S, you can call that S of t. It's a vector as a function of time. But that's going to give you an ordered pair, and it tells you where you are, where the particle is at any given value of t. So part A, find the velocity vector at t equals 1. So whenever it says vector, that just means you're going to package it as an ordered pair. Okay? Find the velocity vector at t equals 1. All right, so how am I going to do that? Well, let's go ahead and first find the velocity vector. The velocity vector, as a function of time, is just like before, it's the derivative of position, right? It always has been. The derivative of position is velocity. The only thing is, we have to do it twice. We have to do it once for the x, once for the y. So what's the derivative of the x coordinate? 3t squared minus, or plus, sorry, 8t, good. And then we've got 4t cubed minus 3t squared. Yeah, so the derivatives aren't going to be anywhere near as elaborate as they were when we were studying derivative rules. So there is your velocity vector function. So now for any value of t, you can figure out what the two component velocity vectors are. We want to figure out what it is at 1. So using the proper notation, v of 1 or s prime of 1. You need at least s prime. You had the option of putting v. And now you just plug it in. It's 3 plus 8, which is 11, and 4 minus 3, which is 1. So whatever the path of this thing is to the coordinate plane, at that moment, most of its energy is being translated to the right. It's going to the right 11 times faster than it's moving up. But it's actually not traveling horizontally or vertically. It's traveling through a curve, okay? So look at part B. Now it says to find the speed of the particle at t equals 1. How am I going to find the speed if I have the velocity vector? Yeah, we would call it this, which looks like the absolute value, but remember, in vector form, we call it the magnitude or the norm, and you can put 1 or 2 bars there. I'll just stick with the 1. How do we find it? Here's what this vector would look like. If you wanted to see what the velocity component vector is, you can actually draw a vector in the x-axis that has a length of 11, because the length of a vector is the magnitude, and it's going up 1 unit, so very small. So if you connected then the tail to the head, that line that I drew in pink would end up being the tangential velocity. That's the actual distance that this particle is traveling at that moment, and the length of that vector is its speed. So again, how do we find that if I know that this length is 11 and that length is 1? Pythagorean theorem. And what's nice about the vector addition is you can move these vectors, well, I didn't want to grab that, but you can move these vectors around anywhere in the coordinate plane, and it's not going to matter. So you can always kind of bring a vector back to the origin, and it just kind of makes it easy, all right? Because as long as they're parallel to each other and the lengths are the same, it's still the same vector. So yeah, by the Pythagorean theorem, this is the square root of, the speed is the square root of 11 squared plus 1 squared, which is the square root of 122. All right, so the speed, or the norm, or the magnitude of the vector, the absolute value essentially, is a single number that represents the length of the hypotenuse from those two numbers there. So the vector is 2 coordinates, the speed is a single coordinate. It's traveling at a square root of 122 units per time in that direction. All right, that's it. We're not going to simplify it. So far, so good? Yeah, okay, good. We could even figure out the acceleration vector if we wanted by taking the derivative of that, but this question didn't ask us. All right, let's look at this one. No calculator. A particle moves in the xy plane, so parametric slash vector, so that x is equal to that and y is equal to that from 0 to 2 pi. Find dy dx and the second derivative. Oh, it did. Oh, part C, the acceleration vector at t equal. Thank you. Yeah, we might as well. So since I called my velocity vector v, I can now say v prime. And again, if you want to name it a, you can. So it's the same idea. You got position, velocity, acceleration, and they're derivatives of each other. So as a vector, I'll just take the derivative of my 2 component velocities. So the horizontal acceleration vector is 6t plus 8. You okay with that? For the x-coordinate, and then 12t squared minus 6t. So just 2 little power rules. And now it's said to evaluate it at 1, so the acceleration vector at 1, you plug in and you get 14, 6. And now you could do kind of the same thing. You can find the norm of the acceleration vector. But do we actually have a name for that? Like speed? No, we really don't. We've never had one, right? The absolute value of velocity is speed. So velocity is just speed in a direction. Acceleration is still a vector, but I don't know, as far as I know, there's not a name for its magnitude. So, but anyway, we can still find the norm. of that by using the Pythagorean theorem, and that would give us the acceleration in a particular direction as a single number. But typically you're not asked that. Okay, so you're just asked to find the acceleration vector. Okay, so now I guess, are there any questions on A? Did I cover everything? I think so. Okay, number 9. This one says to find the first and the second derivative with respect to x. Is there anything in here that would require us to write it as a vector? No. So this one is going to be more like straight up parametric. How do we find dy dx in parametric form? Y prime of t over x prime of t. Yeah, very good. So, and they're given separately. So let's go ahead and find it. Y prime is going to be -2 cosine. And x prime is going to be +4 sine. Now that probably wouldn't be an answer choice because I think that simplifies pretty nice. That simplifies to -1/2, and of course, what's cosine t over sine t? Cotangent, yeah, cotangent of t. So that is going to be the equation that gives you the slope of the tangent line, the vertical with respect to the horizontal, not with respect to time. But notice it still is a function of t. And then to review from yesterday, if you want to find the second derivative in parametric form, how are we going to do that? If I already have the first derivative, how do I go from the first to the second? I take the derivative of the first derivative. Let's see what over x prime. Yeah, every time we take a subsequent derivative, we have to keep dividing by x prime, which is 4 sine of t. So let's keep that in mind. So this did help to simplify, so we don't have to use the Hody-High rule. So what's the derivative of cotangent? Cosecant squared. Negative, right? Negative cosecant squared. So the negative times the -1/2 becomes +1/2 cosecant squared. And then I divide that by another x prime, which is 4 sine of t. So if I'm going to simplify that, what's 1/4 of a half? An 8. And if I bring the sign to the top, it becomes another factor of cosecant. That could become cosecant cubed of t. Or 1/8 sine cubed of t, either one. So something like that makes a fantastic multiple choice question. And guess what? This is certainly going to be one of the answer choices, but guess what another answer choice would be? Just the numerator, yeah, for someone who forgets to divide through by another dx dt. Okay? So we could have easily have done this as a vector equation or vector problem, but it didn't say anything there that we needed to. All right, part B, same question. The path of the particle intersects the x-axis twice. The path of the particle, so it's moving through the xy plane, it intersects the x-axis twice. Why don't an expression that represents the distance traveled by the particle in between the two x-intercepts? Do not evaluate. Okay, this is great. What do I know about anything that crosses the x-axis? Here's the x-axis. So we have something that's moving something like, I don't know, like that, and then maybe it's doing that. So it intersected once over here and once over there, and we would be trying to figure out what this length is. What do we know about anything that touches or crosses the x-axis? We know its y is 0. Very good. So to figure that out, we're going to set y equals 0. Well, we have the equation for y right up here. It's 1 minus 2 sine of t. 1 minus 2 sine of t. Excellent. Now, without a calculator, you're going to be expected to solve that using the unit circle. Great. So 1 equals 2 sine of t, which means sine of t equals 1/2. And now it's unit circle time. We're looking at, it says up here between 0 and 2 pi for our t values. So again, that's kind of in the comfort zone. That's once around the unit circle. So there should be 2 values, right? What are the 2 angles then where t equals 1/2? Positive 1/2. Pi 6, very good. And it's another pi 6 in quadrant 2. That'd be quadrant 4. That's where sine is negative 1/2. 5, yeah, 5 pi 6. Good. 5 pi 6. So there they are. Pi 6, and that's going to be real important. We'll be using the unit circle a lot like that when we get to polar in the next section. So now I can rephrase the question. I'm really now just trying to find the arc length, or the distance traveled by this particle from pi 6 to 5 pi 6, right? So what do we need for the formula? Well, let's call it L. It's going to be the sum now from pi 6 to 5 pi 6 of the speed function, which is the square root of x prime squared plus y prime squared. That's your parametric arc length. It's also the distance traveled, because there's your speed function, right? Do we already have those two functions? Yeah, we already found them over here. So I can just bring those on down. So it becomes the square root of 4 sine of t squared plus the y would be the numerator, negative 2 cosine of t squared. And I put dx, is that right? Nope. It's with respect to t, so I'll fix that and bring my integral down. And there you go. Do we now set out to evaluate it? No, it says do not evaluate it. Yeah. So for a non-calculator question, if they say don't evaluate it, it means it's probably not going to be something that we can easily manipulate and integrate by hand. But if we had a calculator, it wouldn't be too bad. Let's see if this were a multiple choice question and it said which of the following gives the distance traveled along the path. That would not be the answer. If we simplify the radicand, that would be 16 sine squared, and then it would be what? Plus or minus 4? Plus 4 cosine squared. Yeah. And what they might do, what you could also do, is you could use Papa Pid. You could replace cosine squared with 1 minus sine squared and distribute the 4 and combine like terms. You can write the radicand exclusively in terms of either sine or cosine. Let's do that. This is all multiple choice playing around here. 16 sine squared of t, that would be plus 4, 1 minus sine squared of t, using Papa Pid. And now if I distribute, I'm going to get a 4, and I'll have minus 4 sine squared. So the 16 sine squared minus the 4 sine squared can turn into a plus 12 sine squared of t dt. And then, since that turns out so nicely, I doubt that would be an answer choice, because what can we factor out from each of those? A 4. And if we factor out a 4, that's significant because 4 is a perfect square. So I could take the square root of 4 and call it 2 and pull it out front and say pi 6 to 5 pi 6, and then just be left with 1 plus 3 sine squared of t dt. And that could be a nice simplified integral. That could be an answer choice. All your answer choices would be integrals. So again, playing around algebraically with something. If we had to do it by hand, we would be doing all that anyway to see if we could actually get any further than that. But that one we can't find the antiderivative of. Okay, so far so good. That's the end of this section. You like parametrics? You like vectors? Just doing it twice. It's a little bit more interesting because you don't have to just stay on a straight line when you're moving around. Okay, so that concludes this section. Let's go ahead and download the next section, which is really the same idea, except we're going to be using integrals now. This was all about introduction and derivatives. The next section, 7.2, is now about integrals, which is accumulation.